After the remarkable success of Bohr's atomic model, scientists realized that it could accurately explain only hydrogen and other electron atoms. As research in atomic physics advanced during the early 20th century, many experimental observations could no longer be explained by Bohr's theory. Multi-electron atoms showed much more complex behavior, and new discoveries revealed that electrons behave in ways that classical physics and Bohr's simple planetary model could not describe. To solve these problems, a completely new theory was developed, known as the quantum mechanical model, also called the modern atomic model. This model, developed mainly during the 1920s by scientists such as Erwin Schrödinger, Werner Heisenberg, Louis de Broglie, Max Born, Wolfgang Pauli, and others, is the currently accepted model of the atom and forms the foundation of modern chemistry, atomic physics, quantum physics, and materials science. Unlike earlier atomic models, the quantum mechanical model does not describe electrons as tiny particles moving in fixed circular orbits around the nucleus. Instead, it treats electrons using the principles of quantum mechanics, a branch of physics that explains the behavior of matter and energy at extremely small scales. At the atomic level, particles do not always behave according to the rules that govern everyday objects. Instead, they exhibit unusual properties that can only be understood using quantum theory. One of the most important ideas introduced by the quantum mechanical model is the concept of wave-particle duality. According to this principle, electrons behave both as particles and as waves. This idea was proposed by the French physicist Louis de Broglie in 1924. Before de Broglie, scientists believed that light sometimes behaved like a wave and sometimes like a particle. De Broglie extended this idea by suggesting that matter itself also possesses wave-like properties. Therefore, an electron is neither simply a tiny particle nor simply a wave. It has the characteristics of both. The wave nature of electrons was later confirmed experimentally through electron diffraction experiments. These experiments showed that electrons can produce interference patterns, a behavior that only waves exhibit. At the same time, electrons also possess mass and electric charge like ordinary particles. This dual nature is one of the most fundamental concepts in quantum mechanics and plays a central role in the modern understanding of atomic structure. Another revolutionary concept introduced by the quantum mechanical model is the Heisenberg uncertainty principle, proposed by the German physicist Werner Heisenberg in 1927. This principle states that it is impossible to determine both the exact position and the exact momentum of an electron at the same time. The more accurately we know an electron's position, the less accurately we can know its momentum, and vice versa. This uncertainty is not caused by poor measuring instruments. It is a fundamental property of nature itself. Electrons are so small and behave in such unusual ways that they cannot be described as moving along perfectly defined paths like planets orbiting the sun. As a result, the idea of fixed circular orbits proposed by Bohr is no longer valid in the modern theory, because the exact path of an electron cannot be determined. Scientists describe electrons using orbitals rather than orbits. An orbital is a three-dimensional region around the nucleus where there is a high probability of finding an electron. Instead of saying that an electron follows a precise path, quantum mechanics tells us only where the electron is most likely to be found. This is why the illustration shows electron probability clouds surrounding the nucleus. These clouds do not represent the physical shape of the electron itself. Instead, they represent regions where the probability of detecting an electron is greatest. Areas where the cloud is denser indicate a higher probability of finding the electron, while less dense regions indicate lower probability. The mathematical description of these probability clouds was developed by the Austrian physicist Erwin Schrödinger in 1926. Schrödinger introduced the famous Schrödinger wave equation, one of the most important equations in modern physics. Instead of calculating the exact path of an electron, the equation calculates a mathematical function called the wave function. represented by the Greek letter. The square of the wave function gives the probability of finding an electron at a particular location around the nucleus. This probability interpretation was later explained by the German physicist Max Born. Therefore, the quantum mechanical model is often called the probability model or the electron cloud model because it predicts where electrons are most likely to exist rather than specifying exact trajectories. The quantum mechanical model also introduced the concept of atomic orbitals, each having a specific shape. The simplest orbital is the s orbital, which has a spherical shape around the nucleus. The p orbitals have dumbbell-shaped distributions. The d orbitals have more complex cloverleaf shapes, while the f orbitals possess even more complicated structures. These orbital shapes determine how atoms bond together, how molecules are formed, and why substances have different physical and chemical properties. Although electrons no longer move in fixed circular paths, they still occupy quantized energy levels, an important idea inherited from Bohr's model. The difference is that each principal energy level now contains one or more orbitals of different shapes and energies. Electrons occupy these orbitals according to the Aufbau principle, the Pauli exclusion principle, and Hund's rule, which together determine the electron configuration of every element. The Aufbau principle states that electrons fill the lowest energy orbitals first. The Pauli exclusion principle, proposed by Wolfgang Pauli, states that no two electrons in the same atom can have the same set of 4 quantum numbers. Therefore, each orbital can hold a maximum of 2 electrons. And these electrons must have opposite spins. Hund's rule states that electrons occupy orbitals of equal energy singly before pairing up. These 3 rules together explain the arrangement of electrons in atoms and the periodic behavior of the elements. One of the greatest strengths of the quantum mechanical model is that it successfully explains all atoms, not just hydrogen. Unlike Bohr's model, which works well only for 1 electron atoms, quantum mechanics accurately describes atoms containing many electrons. It explains their electron configurations, spectra, magnetic properties, chemical bonding, periodic trends, atomic sizes, ionization energies, and countless other properties with remarkable accuracy. The quantum mechanical model also explains why different elements have different chemical behaviors. The arrangement of electrons in orbitals determines the number of valence electrons, the types of chemical bonds an atom can form, and its position in the periodic table. Nearly every chemical property of an element arises from the quantum mechanical behavior of its electrons. This modern theory is also essential for understanding molecules. When atoms combine, their atomic orbitals overlap to form molecular orbitals, which explain the formation of chemical bonds. Covalent bonding, metallic bonding, resonance, hybridization, and molecular geometry are all based on quantum mechanical principles. The applications of the quantum mechanical model extend far beyond chemistry. Modern electronics, semiconductors, lasers, magnetic resonance imaging, transistors, integrated circuits, quantum computers, solar cells, LEDs, superconductors, and nanotechnology all depend on quantum mechanics. Nearly every modern technological device is built upon principles that originate from the quantum mechanical model of the atom. Although the quantum mechanical model is the most accurate description of atomic structure available today, it is mathematically much more complex than earlier models. Solving Schrödinger's equation exactly is possible only for the hydrogen atom. For larger atoms, scientists use advanced approximation methods and powerful computers. Nevertheless, the predictions of quantum mechanics agree extremely well with experimental observations, making it one of the most successful scientific theories ever developed. It is also important to understand how the atomic models evolved over time. Dalton proposed that atoms are solid, indivisible spheres. Thomson discovered the electron and proposed the plum pudding model. Rutherford discovered the atomic nucleus and showed that atoms are mostly empty space. Bohr introduced fixed quantized energy levels to explain atomic stability and hydrogen spectra. Finally, The quantum mechanical model replaced fixed circular orbits with probability-based orbitals and provided the most accurate description of atomic structure. A useful way to compare Bohr's model and the quantum mechanical model is to imagine predicting where a bird is flying. Bohr's model assumes the bird follows a perfectly fixed circular track around a tree. The quantum mechanical model, however, recognizes that the bird flies unpredictably within a certain region. Instead of specifying its exact path, we can only identify the regions where it is most likely to be found. Similarly, electrons do not travel along fixed circular orbits. They exist within probability clouds called orbitals. So, always remember the main ideas of the quantum mechanical model. Electrons exhibit wave-particle duality, behaving as both particles and waves. The exact position and momentum of an electron cannot both be known simultaneously, according to Heisenberg's uncertainty principle. Electrons do not move in fixed circular orbits. Electrons exist in orbitals, which are probability regions surrounding the nucleus. The Schrödinger wave equation mathematically describes the behavior of electrons. Electron configurations are determined using the Aufbau principle, Pauli exclusion principle, and Hund's rule. The model successfully explains the behavior of hydrogen as well as multi-electron atoms, chemical bonding, periodic trends, atomic spectra, and many other properties. This is why the quantum mechanical model is regarded as the currently accepted atomic model. It incorporates the successful ideas of earlier theories while correcting their limitations. It provides the most complete and accurate description of atomic structure available today and serves as the foundation of modern chemistry, quantum physics, materials science, nanotechnology, electronics, medicine, and countless other scientific and technological fields. It represents the culmination of more than a century of experimental discoveries and theoretical advances, making it the cornerstone of our present understanding of the microscopic world. Electrostatic force is one of the most fundamental forces in nature and plays a crucial role in determining the structure and stability of atoms. Every atom is made up of tiny charged particles called protons, electrons, and neutrons. Among these particles, protons carry a positive electric charge, electrons carry a negative electric charge, while neutrons have no electric charge and are therefore electrically neutral. Because protons and electrons possess electric charges, they exert forces on one another. This force is known as the electrostatic force, which is the force of attraction or repulsion between electrically charged particles. Electrostatic force was first described mathematically by the French physicist Charles-Augustin de Coulomb in the 18th century. His work led to Coulomb's law, which states that the electrostatic force between two charged particles depends on two main factors: the magnitude of their charges and the distance between them. Larger charges produce stronger forces, while increasing the distance between the particles weakens the force. In simple terms, charged particles that are close together interact much more strongly than particles that are far apart. One of the most important rules of electrostatics is that opposite charges attract each other, while like charges repel each other. This simple rule explains many phenomena inside and outside the atom. A positively charged proton attracts a negatively charged electron because their charges are opposite. On the other hand, two positively charged protons repel each other because they carry the same type of charge. Similarly, two negatively charged electrons also repel one another. Inside every atom, the nucleus contains positively charged protons along with electrically neutral neutrons. Surrounding the nucleus are negatively charged electrons. The attraction between the positively charged nucleus and the negatively charged electrons is produced by the electrostatic force. This attractive force is responsible for keeping electrons bound to the atom. Without this attraction, electrons would simply fly away into space, and stable atoms would not exist. Imagine placing a small magnet near another magnet with opposite poles facing each other. They pull toward one another because opposite magnetic poles attract. In a similar way, positive and negative electric charges attract each other. Although electric forces and magnetic forces are different phenomena, this simple comparison helps us visualize why electrons remain around the nucleus. The attractive electrostatic force between protons and electrons is extremely strong at the atomic scale. Even though electrons move with very high speeds around the nucleus according to quantum mechanics, the electrostatic attraction continuously pulls them toward the positively charged nucleus. This balance between the attractive force and the quantum behavior of electrons allows atoms to remain stable. Now consider what happens between particles carrying the same type of charge. Since every proton has a positive charge, each proton repels every other proton inside the nucleus. According to Coulomb's law, this repulsive force should cause the nucleus to break apart because the protons are packed very closely together. Likewise, electrons in the electron cloud also repel one another because they all possess negative charges. This raises an important scientific question. If protons repel each other so strongly, why does the nucleus remain stable instead of flying apart? The answer lies in another fundamental force of nature called the strong nuclear force. This force acts only over extremely short distances inside the nucleus and is much stronger than the electrostatic repulsion between protons. The strong nuclear force binds protons and neutrons together, overcoming the repulsive electric force and keeping the nucleus intact. Therefore, inside the nucleus, two forces are constantly acting simultaneously. The electrostatic force tries to push positively charged protons apart because like charges repel. At the same time, the strong nuclear force pulls the protons and neutrons together. In stable atoms, the strong nuclear force is stronger than the electrostatic repulsion, allowing the nucleus to remain stable. Electrons also experience electrostatic repulsion from one another. Since all electrons carry identical negative charges, each electron repels every other electron. However, because electrons occupy different energy levels and atomic orbitals around the nucleus, this repulsion does not cause them to fly away from the atom. Instead, quantum mechanical principles and the attractive force of the nucleus determine how electrons are arranged in different orbitals. The electrostatic force also explains why atoms form ions. Consider a sodium atom. Sodium has one electron in its outermost shell. The positively charged nucleus attracts this electron. But because it is relatively far from the nucleus and shielded by inner electrons, the attraction is comparatively weak. As a result, sodium can easily lose this outer electron, forming a positively charged sodium ion, Na. Now consider chlorine. Chlorine has 7 electrons in its outermost shell and needs only one more electron to achieve a stable electron configuration. Its nucleus strongly attracts an additional electron. When chlorine gains one electron, it becomes a negatively charged chloride ion, Cl. The electrostatic attraction between oppositely charged sodium and chloride ions then forms the ionic compound sodium chloride, commonly known as table salt. Electrostatic force is also responsible for the formation of chemical bonds. In ionic bonding, oppositely charged ions attract one another due to electrostatic forces. In covalent bonding, electrons are shared between atoms because each positively charged nucleus attracts the shared electrons. Even in metallic bonding, positively charged metal ions are held together by attraction to a sea of mobile electrons. Thus, electrostatic interactions play a central role in every type of chemical bonding. The strength of electrostatic attraction depends on the distance between charges. According to Coulomb's law, when the distance between two charged particles doubles, the electrostatic force becomes 4 times weaker. This inverse square relationship explains why inner electrons experience much stronger attraction to the nucleus than outer electrons. Electrons in shells closer to the nucleus require much more energy to remove than electrons located farther away. Electrostatic force also explains several important periodic trends in chemistry. As the number of protons increases across a period in the periodic table, the positive charge of the nucleus becomes greater. Consequently, the nucleus attracts electrons more strongly. This leads to smaller atomic size, higher ionization energy, and greater electronegativity across a period. Similarly, as additional electron shells are added down a group, the increased distance between the nucleus and the outermost electrons weakens the electrostatic attraction, producing larger atomic sizes and lower ionization energies. In modern quantum mechanics, electrons are not described as moving in fixed circular orbits. Instead, they occupy probability regions called orbitals. Nevertheless, the electrostatic attraction between the negatively charged electrons and the positively charged nucleus remains one of the primary forces governing their behavior. The shape, size, and energy of atomic orbitals all arise from the balance between electrostatic attraction and the wave-like properties of electrons. Electrostatic forces are not limited to atoms alone. They are responsible for many everyday phenomena. When you rub a balloon against your hair, electrons are transferred from one material to another. The balloon becomes negatively charged, while your hair becomes positively charged. Opposite charges attract, causing the balloon to stick to a wall or causing your hair to stand up. Lightning is another dramatic example of electrostatic forces resulting from the accumulation and sudden discharge of electric charges in clouds. Coulomb's law mathematically expresses the electrostatic force as F(Q)Kr, where F is the electrostatic force, Q and Q are the magnitudes of the two charges, R is the distance between them, and K is Coulomb's constant. Although students may not need to memorize the equation at an introductory level, it is important to understand its meaning. Larger charges create stronger forces, while greater distances reduce the force dramatically. It is also useful to distinguish electrostatic force from the strong nuclear force. The electrostatic force acts between all electrically charged particles and can operate over relatively long distances. It can either attract or repel depending on the signs of the charges. In contrast, the strong nuclear force acts only over extremely short distances inside the nucleus, always attracting nucleons and holding the atomic nucleus together. To summarize the behavior of electrostatic force inside the atom, a positively charged proton attracts a negatively charged electron. Two positively charged protons repel each other. Two negatively charged electrons repel each other. The attractive force between the nucleus and electrons keeps the electrons bound to the atom. The repulsive force between protons is overcome by the strong nuclear force inside the nucleus. Electrostatic force plays a major role in atomic stability, ion formation, chemical bonding, and the periodic properties of elements. In summary, the electrostatic force is one of the most essential forces governing the microscopic world. It determines how charged particles interact, keeps electrons bound to atomic nuclei, influences the structure of atoms, drives the formation of ions and chemical bonds, and explains many physical and chemical properties of matter. Without electrostatic attraction between protons and electrons, atoms could not exist, molecules could not form, and the entire material world around us, including living organisms, water, air, minerals, and everything we see, would be impossible.